All right, today we're putting on our detective hats. Our mission, should you choose to accept it, is to get to the bottom of a really common mystery. How do you make sense of data that's changing all the time? We're going to learn how to spot the hidden patterns and get our data ready to, you guessed it, predict the future. So let's just ask the big question right up front. How do you actually do that? How do you look at something like a stock chart or your company's sales figures and make a forecast that you can actually count on? It's a huge question for sure, but the answer starts with something surprisingly simple. And this is the secret, right here. Before you can even think about looking forward, you have to find some stability in the past. You wouldn't build a skyscraper on shaky ground, right? It's the exact same idea here. You need a solid foundation, a clear signal that isn't getting lost in all the noise. Which brings us to our first case file. Why on earth does our data need to be stable in the first place? Well, think of your raw data as a messy crime scene. It's just stuff everywhere. Before you can figure out what happened, you've got to clean things up and get a handle on the evidence you're dealing with. And this, right here, is the golden rule, straight from the source. Data that's stationary, and that's the key word here, it just means stable, is way easier to work with. It's predictable. Data that isn't stationary, well, that's where our real detective work begins. This one idea is the key to everything else we're going to talk about. So let's meet the main villain of our story, non-stationarity. This is basically data that just won't sit still. It's a moving target. Maybe its average is slowly drifting up, or maybe the swings are getting bigger and wilder over time. This stuff is a nightmare for forecasting because its basic behavior keeps changing on you. Let's break it down super simple. On one side, you have stationary data. Its properties are constant, it's pretty predictable, and it's basically ready to go. On the other side, you've got its chaotic twin, non-stationary data. Its properties are all over the place, it's not predictable, and it's the one that's yelling, "Hey, I need some detective work over here." Okay, so it's time to get our hands dirty. Let's open up the detective's toolkit and start the real investigation. How do we even spot this non-stationarity out in the wild? Well, turns out we have two main tools for finding our first clues. First up is the good old-fashioned time plot. It's exactly what it sounds like, a visual map of our data. This is like taking a quick survey of the entire crime scene. Then we bring out the more advanced gear, the autocorrelation function, or ACF. Now think of this as our forensics kit. This is how we dust for the hidden fingerprints that are going to tell us what's really going on. So let's put that first tool to work. This is a time plot of the FTSE 100 stock index. You don't have to be a data scientist to see what's happening here, right? The line isn't hovering around any kind of stable average. It's just wandering. This first look is our big flashing red light. This data is not stationary. But just eyeballing a chart isn't always going to cut it. We've got to dig deeper, and for that, we bring in our second tool, the ACF. Now, what is that? It's actually a pretty cool idea. It just measures how much today's data point is related to past data points. Think of it as measuring the data's memory. And here's the crucial part. A good, stable series should forget its past pretty quickly. And bam, here it is, the smoking gun. This is the ACF plot for that same FTSE 100 data. See those bars on the left? They show how strong the data's memory is. And look at them. They start off really high, and then they just slowly trail off. That slow decay, my friends, is the classic fingerprint of non-stationarity. It's telling us this data has a memory that's way too long. All right, so our visual inspection and these ACF fingerprints have given us more than enough evidence. We've identified two prime suspects behind all this instability. It's time to unmask them. So our first usual suspect is an underlying trend. This is just a steady, long-term drift, either up or down. Think of a company's sales slowly but surely climbing over several years. Our second suspect is a seasonal pattern. This one's super common. It's any kind of predictable, repeating cycle, like how temperatures always go up in the summer and down in the winter. Both of these guys will mess up our data. Okay, we've identified our culprits. So what now? We can't just throw the data away. Instead, we have some really clever techniques to basically neutralize these effects and clean up the data so we can finally see the real, stable signal that's been hiding underneath. So to handle a trend, our number one go-to move is a technique called differencing.
Now, I know that sounds a little technical, but trust me, it's ridiculously simple. All you do is stop looking at the actual values, and instead, you look at the change from one period to the next. You just subtract yesterday's value from today's value, and you do that for the whole series.
And would you look at that? Here's the payoff. On the left, you see our original ACF plot with that slow trailing decay. That's the before. But on the right, after we do our little differencing trick, wow, what a transformation. That long memory is just gone. The pattern drops off almost instantly. One simple step, and we've stabilized the data.
All right, one culprit down, one to go. Let's talk about seasonality. This plot of monthly temperatures is the perfect example. I mean, come on. You can see that repeating wavy pattern from a mile away, right? It goes up, it goes down, over and over again. It's another classic case of non-stationarity. And the solution here is a really clever twist on what we just learned. It's called seasonal differencing. Instead of subtracting yesterday's value, you subtract the value from the same time in the last cycle. So for this temperature data, you'd compare this January's temperature to last January's temperature. It's brilliant.
And just like that, it's like magic. The big, predictable wave pattern is totally gone. This plot shows the temperature data after we applied seasonal differencing. The pattern has vanished, and we're left with a nice, stable series that we can finally actually analyze.
So, we've covered a lot of ground, and we've established a really clear process here. Let's just wrap up this part of the investigation with a quick reference case file. Think of this as your cheat sheet for your own data investigations.
Here it is, all laid out. It's pretty straightforward, right? If you see an ACF plot that decays really slowly, that's your clue you've got an underlying trend. The solution? Differencing. If you see a repeating wave in your ACF, that's seasonality. The solution? Seasonal differencing. It's a really powerful and systematic way to approach this.
So, by using these techniques, we've successfully interrogated our data. We've peeled away all the distracting stuff, the trends, the seasonality, and we've finally isolated that true, stable signal that was hiding underneath it all. We've done it. We've taken chaotic, unpredictable data, and we've turned it into a stable, predictable signal. Our initial investigation is complete. The case of non-stationarity is officially closed. But, this isn't really the end of the story. Because cleaning the data, as important as it is really just step one. Now that we have this nice, clean, stable signal, we have a whole new question to deal with. Which model is the right tool to actually build our forecast? And that's an investigation for another day.